Okay, now our next topic of discussion is going to be another set of tools within R that allow us, again, even greater levels of control for writing our scripts here. So, so what we've seen so far is that we can use the idea of a function to execute a sequence of commands that we don't know what's happening inside, but we certainly know what we're giving that function, what it's doing, and what we can expect as an output. We may not know how it does things, but we know what it does. And we've already illustrated a few different areas. So as you can see, we used the print function, the read line function, and we've used a few other functions as well, the seq function, so on and so forth. And as it turns out, you can also define your own functions. If there's some functionality or feature that R does not have built into the system, then you can use your own, define your own functions and then use those functions. Functions, as strange as that may sound, may also be used as an input into another function, and we'll get into that small little nuance in a little bit. But before we do, let's get into just the basics of defining a function. So suppose for the moment that you want to be able to run a sequence of commands with some given inputs, assuming that the inputs have been assigned to some values, very similar to how you've used other people's functions. Imagine that someone else is going to use your function, or you'll use your function at a later point in time, but it's repeated code, right? You don't want to have to keep writing the same piece of code over and over and over again. In which case, you want to be able to just quickly execute the code. So for example, suppose that we wanted to write a function that will take a single that will take a single input, namely a number, and it will output some type of mathematical function evaluation as a result. So, for example, suppose we wanted to output the result of e taken to the minus 2 times x minus 5 plus so let's see, e to the minus 2x minus 5 plus, let's say the sine of, or let's say divided by 1 minus x, okay? And so we're just defining a basic mathematical function, and we want to set x equal to, let's say, 5, right? So here we have this function, and as you can see, for different values of x, we're obviously going to get different values for our corresponding y, so to speak, if you want to store those in y. The problem, however, is that this function here is a pretty complex type of expression, and I want to be able to very quickly get the output of that number without having to retype it over and over and over again. And there are a lot of practical situations that arise in your analysis of data, where you'll have similar situations where you want to repeat this, be able to repeat the same function over and over and over again to evaluate it at different points. So instead of having to keep repeating that expression and either storing the results in a variable or a vector, what we can do is just define a function that will basically, in some sense, shorten this up. So the way that we define a function is we start the same way that we define a variable. We give it a name. All right, so let's just call it the function. It could be pretty much anything you want it to be. You can use this assignment, but usually for functions, it's common practice to use the equal sign. Both will work, doesn't matter, but usually, as I mentioned, it's common practice to use the equal sign. This is then followed by the word function, and then we provided a list of inputs that we would like the user who is calling this function to provide to us. So we're going to give it, we're going to write a list of variables which we'll use in our function, and we assume that whoever calls or uses our function, they will provide to us the values, or they will assign the variables we're about to list out here, those variables to numbers, so that we're working basically off of an assumption, excuse me, that all of the numbers here, or all of the variables that we list out inside the parentheses here, are assigned to some number. So basically, we're working in some sense off assumption. With some sense, we did the same thing, right, when we were using functions. When we use functions, we make an assumption. We assume that when we call this command and provide it an input, that R is going to give us back an output. Well, now we're sort of making assumptions in the opposite direction. Rather than the outside, assuming that the inside, rather than thinking of being on the outside and thinking that the inside is going to do our work for us, think of it from the reverse. Think of it that the outside is going to give us information and we're going to do the work. So that's the way we kind of have to think about this. So let's just declare a single input X, and we'll assume that the user will provide us a number to input there. So what we have is when we have this definition here, what we do is we do the same thing that we do in our logical control. We open it up with an open or left and right brace. We call this an open brace and a closed brace, by the way, but doesn't matter in this case. So we open it with an open and closed brace, and then we write our commands that are going to be executed in the function. In this case, we just want to do the expression of this. So there's what we can do is assign this to a variable, and then what we do from here is we write the return commands, the return function, and pass Z through it. What return does is basically take anything that you want to give back to the user who provided or who is expecting a certain type of output. There's two ways to return. The first is to explicitly use the return function, which helps in certain scenarios. The second is to just write whatever it is we want to give back to the user on the very last line of the function. So we can do it either this way or we can do it this way. I personally like to use the return function because it keeps me honest and it's very explicit about what I'm returning back to the user. And so if there's something going wrong with my code, then I can very easily, take a look at it and see if it's working correctly or not. So let's run that. And now, if you were to see, just like you would in any other variable, what's in the function, you'll happen to notice that our function is now in, that variable. So life's good there. But how do we now use our new function? Well, you use it like any other function. You know what the name is, right? Okay, you know what the name is. So just call it the function and give it some numbers, the same numbers that we had before, right? Okay, so there you go. So here, excuse me. Here we're calling the function and providing it different inputs. Basically what R is doing is it's going to look up this function to see if it's defined. If it's not defined, it's going to throw an error at you. Because we just defined the function, it will be in its collection of functions now, just like all of our other functions are. When you call that, it will then take the value 5 and assign it equal to the value of x here in the definition. It will then run through all of the lines of code that are in here, and it will return whatever value is stored in Z. It will then give back that value just like it does in any other function. And so that's basically the nuts and bolts of how the functions work. So as you can see, we're getting the same values that we got before, but we don't need to write the same. I don't think we ran number 1, but we should get infinity, by the way. We're getting the same values as before, but the difference is we don't need to write the complicated function anymore. Since we know we're going to be using that function over and over and over again, we can just use the function. By the way, we can rename functions by storing them into other variable names. So I could do something like this, for example. And now I've basically renamed the same variable. So as you can see, it has the same function definition stored in F. So if I wanted to shorten up a function that I know I'm going to be using, right, I can do that. Another neat thing that I can do is, of course, in function definitions, I can integrate the logical control. And logical control comes very handy to execute certain pieces of code depending on what the input is. So, for example, suppose I wanted to write a function that will plot the data points of a function. So what I can do is come up with another definition. Okay, so plot data points of a function. If you don't know how to plot data points, let me just illustrate this briefly to you. First, let's do just a random sample, which we can do by using a random sample uniformly distributed numbers on the interval of, let's say, 0 and 10. And you can do that by running the runif function. And let's say we sampled 1,000 of those points. Okay. And further, let's say that we have the data points 30 times x plus r norm, which randomly samples data points from a normal distribution, and we'll certainly talk more. We'll certainly talk more about what that specifically does. Let's see. Let's go with 5. I don't know if that's good enough or not. So if you take a peek and look what's in X, I have some X data, I have some Y data. If I want to plot a scatter plot of those, you can use the plot function, where you pass it first the set of X values, and then you pass it the set of Y values. And if you run that function, you'll see that you get a scatter plot of the data points themselves. Of course, I can expect to get something that looks like a line simply because, well, that's how I defined my Y values, right? I have them as the equation of a line with some random scatter. We'll get into more about the random scatter later. But right now, I just wanted to illustrate the use of the plot function. Anyway, suppose I wanted to write a function that will plot the data points of another function. So let's do that. I'll call this plot function, okay? And what we'll assume, again, we do the equal sign function, we give it a list of inputs. Let's assume we have 3 inputs. And I'm sorry, not 3, 2 inputs. The first input that we have are the x values that we would like to plot the function over. So here we'll assume that x is actually a vector rather than a single number. The next that we'll assume is passed to us is the name of a function that we'll call, and we'll call that. And I'll just use a different one, g, just to be clear here because we've already used f. So g here basically is going to go through the same. When somebody gives us a function to use, g here is going to go through a similar type of assignment operation that we did here. It's basically just going to rename that function g so that I can call it anywhere in my code that I'm about to write. It's a very general way of using a function. So there's 2 things that a user is going to give me: the set of inputs in terms of its being in vector form, and the function itself that I'm going to be calling. So what we can first do is compute. The first step in here is to compute the actual values of g, and we can use a for loop. And we can basically say for each I in x, because remember, x is assumed to be a vector, right? So, and what we'll do is we'll create a new vector y, and just store an empty empty vector to that. And what we'll do is on each iteration we'll append to that vector. So we iterate over each value in the independent variable. We set, so remember what for does. It's going to set I first equal to the first element in the vector x. It'll do whatever is in here, go back, set I to the next element, so on and so forth. Pardon me. And basically what I want to do is compute the value of the function at that point. And I'm going to store that in a variable called fun value. So what's going to happen here first in the for loop? It's going to use the function g. We don't know what the function g is, but we are assuming that g has only a single input, which is that it's x. And we're going to pass it through the function. The function is going to compute the value at that point in x and give us back a y value. The y value will then be stored in fun value. We're then going to need to append that y value to a vector. So what we'll do is say store in the variable y a new vector with all the old variables in y with the new function value. When we do this, what's going to happen is we're going to get a new vector of y's which have been evaluated at the function g. We then can plot the x and the y. Here we're returning nothing because plot function is a function where we're not the output that we're expecting is a plot. Okay, so we can assign it to something and then just call the plot, but frankly, what we want to do is just simply plot it. So let's define here. Let's suppose we define 2 functions. Function 1 is going to be defined as the function, let's say e to the minus x squared. And then suppose we have a second function that we define as 5 minus 5 times x squared plus 24. And let's suppose that, oops, sorry, that goes in here, x goes in here. And suppose I want to plot these 2 functions, all right? Now I have two functions which are defined, and I have the plot function itself, which is defined. Now, instead of writing all of this, basically, instead of writing all of this code, where the G would equal one of the F's here, now I have generalized it in a way where I can basically just simply repeat the same code and just say, well, call the function plot function, and pass through the different functions. So for example, independently, what I could have done was, let's see, let me declare these up here. What I could have done was something like this, okay? I could have declared the functions, but then I could have ran this code twice. One for the first function and the second for the second function, right? And if I had more than one function that I'm writing, I can do this a whole bunch of times. So let's first run it for the first function, see what we get. All right, that's pretty cool. Let's do it for the second function. All right, cool. So obviously we get two different plots. We can make the lines look nicer, by the way, by using the input type equals L in parentheses, quotations. And, oh, no, you need to actually order the X, which I don't want to get into just yet. So forget what I just did there. Just look at scatter plot. Okay, so there you have it. Two functions that are plotted. But as you can see, this becomes very frustrating, especially if you have lots of different functions that you've defined and you want to run the function on those different functions. The code, you'll notice, is slightly different here. The only difference being that I'm calling different functions. So the way that I can think about it is there a way to make this more general? And the answer, of course, is yes. We can write the function that we just did here. Basically, what we can do is define a function where the input is the name of a function. And then what R is going to do is replace the actual name of the function, like what we have here, with just G. And it will simply just call that function, assuming the inputs are all, of course, the same. That's a hard assumption to make. You can actually use more general type of functions, but that's getting too far into more advanced coding techniques that we don't really need to get into. So right now, we have a good setup. We've repeated the same code. We've identified the point of difference, and we found a way to generalize it, which is that, okay, just call the function G and assume that the user will pass us a function. So now that plot function has been created, what we can do is call it plot function, the values of X that we have, together with the function F1. And again, what R is going to do is take the function F1, which is what you defined here, and replace it with the name G, so that you can just call that same function F1 by calling it by the name G. And when you do that, you can see that you get the same output, but you didn't need to rewrite the code all over again, because the code has been generalized in a certain way. So when we work with the functions, functions can act as input to other functions. The way that works is basically as like a renaming scheme, where all we're doing is just renaming the function to something else, more general, so that the user can plug in different functions into this. One thing of note before I end our discussion here is on the use of the apply functions in R. And there's a few different apply functions. In this one, I'm only going to talk about sapply, which the purpose of the apply functions is to take a function and apply it to all of the values in either a data frame, a list, or a vector. So for example, suppose that we had the vector x, where what we've done is let's say, well, I just want to shorten it up. Let's say we do the RUnif again, where we have 50 values from 0 to 100, let's say. So take a look in what's x. We have just random numbers that we've selected. And suppose that to each of these numbers, we want to apply a particular function to. Suppose that we want to find we want to apply our function here, like f1. Right now, I think this might actually work. I don't remember, but let's see if this would work if we apply f1. And lo and behold, it does, but this doesn't always work. So another way to apply the function f1 and that's because these functions here usually assume that these are vectors anyway, so of course that would work. In some cases, you're going to run into some problems where you think that you can just run your function, whatever that is, on the whole entire vector, and you might think that the function is going to apply automatically to every element in the vector. That's just not the case. So how then can you apply the function, let's say f1, our function, to every element in the vector? Again, we did it for us automatically, but let's make this more explicitly known how it sort of goes about doing that. What we can do is use a function called the sapply function. And with sapply, you always specify two things. The first thing you specify is the vector on which you want to apply the function to. The second thing that you specify is the function which you want to apply to each individual element. So in this case, let's say I just want to apply the function f1 to each individual element here. If you run the sapply, you'll notice that it gives you back the same thing here, which is good, which meant it was applying this function to each and every input x. That is basically equivalent to writing the code for I and x. Sapply is equivalent to writing this code down here. Create an empty vector for every I and x. Append to the vector f1 of x. You'll notice, obviously, this is much shorter than writing this. So these are equivalent pieces of code. sapply is a little bit faster sometimes, though. So whenever you have a vector that you want to apply a function to each element, you can use the sapply function. You don't need to pass it the name of a function, by the way. You can define a function right in that input if you wanted to. So suppose we wanted to apply to each element x. Remember what's in x here. Suppose we wanted to apply to each element in x a new function whose input is y. We can do that by writing just the word function, input y, open brace, close brace, but make sure that's still in the function itself. And suppose that we want to round each of the numbers. For each number in the vector, we want to round it, and then we want to check if it's even or odd. So let's just do the rounding. Okay. Where we find y. And let me clarify things here. If it's applying this function to every element in x, where x is a vector, basically what it's doing is it's first taking this number, assigning it equal to y, and then applying whatever commands I'm going to write down here. When it's done, it's then going to take this value, assign that equal to y, and do the same thing over and over again for all values in the vector. So under that assumption, we assume that for each value in the vector x, it's assigning y equal to it. We're going to round that to get a rounded number. And then to check if something is even, we just need to check if it's divisible by 2. To check if it's divisible by 2, we can just divide it by 2 and find the remainder to see if the remainder is 0 or not. Because it's going to be divisible by 2 if it doesn't have a positive remainder, right? So what we can do is just simply find the remainder between the rounded number and 2. Remember, this operation finds the remainder. If you don't remember that, right? 5 remainder 2, let's say. This is the remainder after dividing 5 by 2, which should be 1. If you look at, let's say, 7 by 2, right? 2, 4, 6 should give us 1. 7 by 3, 3 and 6 should also give us 1. Remainder by, remainder by 4. 7 divided by 4 goes into 7 one time, and that means there's 3 left. Okay, so this is giving us the remainder. The way you check that a number is even is if you divide it by 2, and if you get 0, then it's always going to be even. If it's 1, then it's not going to be even. Because by definition, even numbers are always divisible by 2. That means, in other words, you can divide 2 into it and get 0 remainder. So what you want to do is you want to check, you want to write the logical statement, is the rounded number divisible by 2? And we're going to basically just ask, is this equal to 0? You'll notice that by writing the double equal sign, it's going to compare or contrast that, right? It's going to say, nope, that's false. Suppose I did 4, that's true. So what it's basically going to do is tell us whether or not that specifically is true or false. So by doing the s-apply, it's going to give us a new vector of true or false values. And lo and behold, it does. So take a peek and see what's in x again here. Rounded, this is 10, which is even, 94, which is even, 52, which is even. This rounds to 69, which is obviously odd, and we obviously see that it's not true to get even numbers. So as you can see, we were able to take the s-apply function and very quickly apply a different function to each individual element, and that function we just happened to define on the fly. So with the s-apply function, very powerful tool. Whenever you have a scenario where you want to apply a function to multiple elements in a vector, where the return elements is basically going to be another vector of the same size, then the s-apply function is a very powerful, useful tool. Getting to learn how to use the s-apply function while defining your own functions will help aid in your writing of code, because it makes things very efficient. Also, as you start to get to more advanced topics like parallel computing, distributed computing, things like this, it helps in being able to very quickly compute these things across multiple different machines all at the same time. So anyway, this is the concept of defining your own functions. We're going to be seeing that we're going to define our own functions on a pretty frequent basis, because we just happen to have a lot of different applications of doing so.